Good afternoon, everyone. Good afternoon, good afternoon. I guess we are at an academic institution because no one sits in the front. So if I could ask, there are plenty of seats up here in the front, come on. And I've looked at most of the people and they don't look like they bite. No, good, okay, they're so come on up, there's lots of seating up here and in between. So please come on, we don't want anybody to have to stand. I knew we should have assigned seating. I just knew it. Yeah. Okay, please come on up. There's three more here. Do we have three volunteers? Two over there. We have seats for everybody. I just want to make everybody aware there are lots of seats and people will be perfectly willing to welcome you and show you where those seats are. So please come join up in the front. I want to welcome everybody this afternoon. I'm Shelley Schuster. I'm the president of KGI, and it is my pleasure to welcome all of you here today as we continue our 25th anniversary celebration. As most of you know, we are an institution that it is the newest of the Claremont colleges. We began with one program 25 years ago. We have 17 programs at the moment, growing, innovating, and making an enormous impact on the life sciences and healthcare industry. We are extraordinarily proud of everything we have done. Before we begin, I'd like to introduce a few of our distinguished, that's a word, right? Distinguishes visitors and guests. Let me start with our board chair, Jim Wittergren and Denise Wittergren. Let me second say we have the Home Secretary of the National Academy of Sciences, whose bigger job is, she is my wife, and that is more than full-time. So Susan Wessler. And no, she does not get hazard pay for that. She should, yeah. And let me also introduce Dr. Tony and Dr. Virginia Chan, who are major supporters of graduate and students. One of the real reasons I want to also introduce you to them is because you are all invited to the Chan Family Cafe afterwards for a celebration, a networking event, and a chance to celebrate with our speaker and celebrate our 25th anniversary. So it is a thrill to have all of you here. Everyone, I apologize for those I'm not recognizing. But I do want to begin, and I'd like to first start out. We have a very short video because otherwise I will wax philosophic about our history. So let's have a very short upgrade of who we are, and then we'll begin.
Hank had a vision. He had a vision of the engineering education model applied to biology. He had a vision of applied life science, of starting an institution that would be unique in that the only thing it did was applied life science. And he stayed focused on that all the way through, no matter what people said.
In the beginning, the forefathers of this place decided that we're going to create leaders in this industry. One of the best things they did, in my opinion, was combine the MBA-type courses and the biosciences courses.
He had a vision of the engineering. Hank had a vision. He had a vision of the engineering education model applied to biology. He had a vision of applied life science, of starting an institution that would be unique in that the only thing it did was applied life science. And he stayed focused on that all the way through, no matter what people said.
In the beginning, the forefathers of this place decided that we're going to create leaders in this industry. One of the best things they did, in my opinion, was combine the MBA-type courses and the biosciences courses.
The Keck Foundation had connections to the Claremont colleges. They were willing to make an investment in something that was good, something that had promise, and something that would change everything. And there's no question in my mind KGI and its curriculum and its approach changed everything with regard to education in applied life sciences.
I'm very confident that the initial approach that we had when we started this institution, that the education was going to be team-based, hands-on, and real-world, is very, very unique and special.
What President Schuster has done is provided kind of visionary, forward-thinking leadership that an institution has to have. And I think most institutions are backward-looking, and he is willing to take cutting-edge ideas and go forward with them and be brave enough to think about having those ideas and then to pursue those ideas and make them into reality.
Our faculty are deeply committed to the success of our students. They go the extra mile, whether that's going on countless trips to companies for our projects, to designing a state-of-the-art curriculum, to teaching a variety of areas. They're just tremendous.
Every student who comes here because they have a specific plan in mind. They all want to, again, make a difference, be leaders. They have such motivation, enthusiasm, positive attitudes. It's really a joy to interact with those students.
We're growing very steadily right now. We have programs that are having major impact. Our brand is increasing. We're getting just outstanding students from all over the world. So I see ourselves increasing our impact dramatically in the next few years.
I'm very excited about KGI. KGI has the opportunity to be the leader in life science education here in the United States.
It's been just a tremendous first 25 years for KGI, and we're excited to continue to lead and innovate over the next 25 years.
Thank you. It's now my pleasure to introduce our 25th anniversary speaker, Dr. Stephen Kingsmore. Stephen comes to us by way of Belfast, Queen's University in Belfast, where he got his initial training as a physician and mostly studied immunology. He did a residency at Duke, and then he had the either fortune or misfortune where he and I worked together for a long time at the University of Florida, and he was one of the pioneers in what at the time was calling next-gen sequencing. For some companies that some of you may recognize, like Curigen. He was one of the original kind of folks. He moved on. He came back out here to the West by way of Kansas City, Missouri, where he's head of a Children's Genomic Institute as well. He is now the president and CEO of the Rady Children's Institute for Genomic Medicine, where there is a multidisciplinary team of science doing some extraordinary work that he's going to tell us about, using whole genome sequencing as a clinical and diagnostic tool. Steve has many accomplishments, and I won't list them. I'm hopefully he's going to tell us a little bit more about some of the things that he's doing these days. But I will say that he is the only person in the world that I know who is in the Guinness Book of World Records. He and his team have achieved the fastest molecular diagnosis using whole genome sequencing in 19.5 hours. And it's quite an accomplishment, especially when you think about the need for these kinds of things with young infants and babies. So it is my pleasure to introduce my dear friend, Steve Kingsmore.
Thank you, Shelley. Great to be here. I haven't been here since before COVID, and it looks like you got some new buildings since I was last here. All right, so I'm going to try and sit on this wobbly chair. It's going to be fun. Shelley helped me set up a company at the University of Florida called Gazergen a long time ago, so we go way back. All right, so the title, because it's your 25th anniversary, is kind of a recap of the first 10 years of genome-informed healthcare delivery for kids, which is what I do. And then at the end, we'll look forward to what I think the next 10 years is. I was encouraged to do 25 years, but this has only been around for 10 years. So 25 years ago, there'd be a 50-year nothingness. And for the life of me, I can't look forward beyond 10 years. I just have it in me. Okay, next slide, please. Okay, so the healthcare system today, tragically, is broken for children with genetic diseases. And the statistics you can see there. What you can't really see is what that means. Can you imagine being a mom or a dad and having a child have a rare disease, potentially a genetic disease, and you go from specialist to specialist over a period of years without knowing what's going on? You don't have an answer. I don't know, most of you are young, but those of you who are more my age, you'll know how difficult it is to see a subspecialist. You don't just call them up and wander into their office. You have to be referred. There's a waiting list. Well, these parents and families go through this for about 5 years. Now, many of them never receive a diagnosis. And those who do, tragically, by the time a diagnosis is made, we're so far into the disease that even if there is an effective therapy, it's too late. A great example is spinal muscular atrophy. I'll just diverge immediately on slide 1. Little baby, mom and dad bring him to the Hotel del Coronado in San Diego for a vacation. New baby. He's floppy. They've known that, but he gets a respiratory infection, winds up in our emergency department, winds up in our intensive care unit. We diagnosed him, and I'll show you how, almost immediately with a genetic disease called spinal muscular atrophy. Now, spinal muscular atrophy is one of the rare diseases where we can cure it. We can give gene therapy. It's very expensive. We can give gene therapy, which replaces the missing copy of the gene, and you're cured. However, he has an irreversible defect. His anterior horn cells, which are responsible for initiating movement, are dying. And by the time we see him, it's too late. He won't benefit from that therapy. He will die before age 2. That's the tragedy today, that even in an era of gene therapy availability, something that we wanted all of our adult lives, we still have these tragic situations. So today we're going to focus in on that and see what we're doing to make that a thing of the past, to retire this concept, this term, diagnostic odyssey, and then look forward to where the field is going. And one thing, I put a very important point in there. Some of you I know aspire to go to medical school. It's a great aspiration. One of the mantras you'll be taught is when you hear hoofbeats, think horses, not zebras. What does that mean? It means don't chase rare and ultra rare diagnoses. When you see a symptom or a sign in a patient, as you formulate your differential diagnosis to identify the etiology of their complaint, think about the common things first. This works well for common complex disease. It works against these families and children. And it means that we are running against the tide of what is pummeled into every young medical student and every resident. Next slide, please. This is a complicated slide, but it's kind of the thrust of the idea. So let's walk through it. So Fitz is a little boy, again from Coronado, who also got gene therapy. We'll come back to him in a minute. So at admission to our hospital, Rady Children's Hospital, San Diego, Children's Hospital, Orange County, Loma Linda, wherever you are, about 50% of children will have a disease of unknown etiology. We're not sure why they're there. We need a diagnosis. We need an answer. The traditional way of doing this is that differential diagnosis list, common stuff on top, rare stuff probably not even on the page, and you start working through this. Now, in an outpatient setting, if you've got a slowly progressive illness, that's going to be okay. You just keep going around the circle. If you're in an intensive care unit, you may well die before an answer is arrived at. So about a decade ago, we had the idea, why don't we just decode the genome? Would that be possible? Could we do it in a day? And that's the bottom pink line. Could we, as a first-tier test, at admission, order a genome and get an answer? Would it work? Would it change outcomes? Next slide. So this was the pivotal paper. It came out in 2012. Up until then, I had had a somewhat inauspicious career, no Guinness World Records. But the day that came out, paper was on the front cover of the New York Times. And that evening, I was on PBS NewsHour. And suddenly LinkedIn had me numerous individuals, most of whom only wanted to sell me stuff. So the world changed then. This was one of the first times when genomes, and remember we decoded the first human genome in 2003, it had taken over $1 billion, many, many years, 15 years, and it had held tremendous promise. This was the first time it became tangible. A baby in an intensive care unit, a genome in this case in 2 days. Next slide. So let's fast forward from 2012 to today. What have been the key trends? Well, there are three on this slide. Number one, our knowledge of genetic diseases has gone through the roof, largely through NIH support in the US and other organizations worldwide. We have identified thousands of new genetic diseases, and the number now stands at 7,300. We can't precisely count them because that's the number in our leading database, Mendelian Inheritance in Man at Johns Hopkins, but there are probably another 5,000 or 6,000 who aren't in that database. And it continues to rise. Every morning, there are fresh diseases added to our list. As a doctor, this makes it impossible to keep up, impossible to contain that information in your head. Second of all, Shelley mentioned the Guinness World Record phenomenon. This is something we've chased for a decade. That first 48-hour genome was not recognized with the Guinness World Record. The second and the third were, and so we hit 2 Guinness World Records. And then, oh dear, this time last year, a little bit later, March last year, our Guinness World Record was shattered by you and Ashley at Stanford. You set a new benchmark of roughly 7 hours. And as you can see there, well, still on 7 hours, but Danny Miller at the University of Washington did something similar recently, still not published, 3 hours. So the idea of decoding a genome and getting a doctor and a family an answer in a day, that idea is easy. Then lastly, this started out to be incredibly expensive. The first human genomes, I told you, cost over $1 billion. We now, within the next year, 18 months, will have availability of $100 genomes. You know, some of you spend more on coffee each week than that, right? Some of you who are over 18 spend more on alcohol per week than that. So what this means is they're going to become abundantly prevalent. Next slide, please. Okay, let's talk about a story. So mom and dad, I'm going to wander down where I can see this. Mom and dad, is that going to drive you crazy on the camera? Yes, good. Excellent. I'll even turn my back to you if you're not nice. So this is a 5-week-old little baby boy. Mom and dad bring him into the emergency department. Actually, it's mom who brings him. And the complaint is fairly benign. I can't console my baby. What the nurses rapidly realize, though, is this baby is extremely irritable. In fact, he's what we call borderline encephalopathic brain irritation. And of note, as is true in San Diego a lot, and also up here, we have ethnic diversity. This family traces their origin, at least they're actually first cousins. Next slide. So, of course, he gets admitted, he gets a CT scan to image his brain, and it's very abnormal. Let's do a click, please. So this is 11:18 p.m. A, B, and C on the left are his brain, and that white stuff is abnormal. His brain shouldn't have that. Those are fluffy white lesions, hypodense lesions. Could you click again, please? And this looks like what we call hypoxic ischemic encephalopathy. Remember the hoofbeats? The hoofbeats for a horse. This is HIE, hypoxic ischemic encephalopathy. Treatment for that is you cool the baby down to try to preserve their brain function. This is not HIE. This is a zebra. You give that treatment, this baby will die. So instead, next click, we take a history and we get some more information. Let's not forget that that's kind of important. Now, dad arrives. Mum, because of her Middle Eastern background and stuff, is a little reticent about the family history. Dad amplifies the information and tells us, you know what? He had an older sister in your NICU, arrived exactly the same age, exactly the same presentation, died after a 1-year illness. So we, of course, go look up the CT scan and MRI on the sister, and that's shown in D&E. Looks like his older sister, a decade earlier, had the same disease. They're consanguineous. I think a recessive condition that runs in the family. This is starting to sound like it's a genetic disorder. And this really points out what's happened in a decade. A decade ago, no answer, no possibility of treatment. This baby might just. Next slide. So we get that information, we filter this, and we want a genome, please. Slide. I got a lot of clicks here. So the genome is ordered. We have to get mom and dad to agree. We need blood samples, get them over to the lab. Next click. And by 7:30, as you can see, we have genomic DNA on a sequencing instrument in our lab. Next click. Now, in the meantime, the baby has a rough course. He's starting to recapitulate what went on in his older sister. He started to see. These are artificial intelligence tools. This is a 13.5-hour genome. This made the New England Journal of Medicine, because by 7:30 a.m., that's 7 plus about 31 hours after he was admitted. Next click, we have a diagnosis. It is an autosomal recessive disorder. The name is there, the gene is listed there, the variant is there for those of you who are into this stuff. Next click, most importantly, this is a treatable condition. And all this baby needs is large doses of 2 vitamins, biotin and thiamine. So we order those, crush them up because they come in pill form for adults. There's no childhood formulation. This is a dietary supplement. It's not actually a drug. We started through a tube feed because he's seizing. You can't take bottle feeds. We started, and next click, he's better by 6 p.m. He goes home 3 days later after we've taught mum how to crush the pills and administer them in bottle feeds, and he's doing fine. He likely will have a normal outcome. 10 years ago, a year ago. Next slide. That's what we're trying to do. But we would like to do that in every NICU in North America for every baby who would benefit. That's kind of tough. I don't have time for this next one. It's great. So I'll do it really quick. This is a cheerleader who collapses after supper. Mum starts CPR. Very stormy course. They continues CPR. They defibrillate her multiple times. Transferred to a local emergency department. Winds up eventually in our pediatric intensive care unit. Next slide. We get a genome. This is during COVID, and so everybody's thinking, it's COVID. Next slide. It's not. It's a genetic disease. The disease causes what she has, although this is very atypical. Next slide. She goes on the transplant list the next day. She gets a transplant 3 days later. To my mind, it's the fastest transplant in history. Why is that important? You're not going to get a transplant unless we know what's causing your illness. And if your illness will recur in a transplant's contraindicated. So she would have gone on an assist device. This is what would have happened if we chased the hoofbeats towards a horse. We would have said this is viral myocarditis. We treat it with steroids and intravenous immunoglobulin. We wait a month. Your daughter's going to do just fine. We'll supplement her heart function with a temporary assist device. We'll wait. She would have died. Instead, she got a new heart. And within a couple of days, she was back on her iPhone. And now, presumably, she is back doing this. Next slide. Okay, so since then, what happens? So you invent something that next 10 years, or study after study after study, by group after group after group, recapitulating until you get critical mass and you show that this is the evidence base, that we now have created an evidence base. This is safe, effective, it changes outcomes. Another click. Just some summary statistics on 31 studies, of which we did maybe a third. Next slide. However, nothing changed. NIH said, fed up giving you money, so you can't do any more research studies. It's not proven. Children don't get this. So the next thing that happened, interestingly, was a politician came along and said, why don't we put an act into the California legislature and get you a little bit of money to prove this out for Medicaid? And they did, and we did. And this is the result. We enrolled babies in 5 hospitals around the state, and we showed that this saves money. Why? Because babies are in and out of the intensive care unit much faster. Instead of hanging around for test after test, we decode the genome, get an answer, and then we know the disposition. It's either great, we've got effective therapy, or we don't have a solution, but we do have an answer. We can plan a disposition. So overall, you can see are actually saving. The amount is, you can't really tell from these studies. We would need 30 of them, we haven't got that. It definitely saves money. It doesn't cost money net. Next slide. That's when everything changed. Suddenly the bean counter said, let's do this. It will save us money. And so this is the recent map of the states that have now a Medicaid policy, which means about 60% of kids will be able to get this in those states. Now, some states were enlightened, and funnily enough, it was a state like Michigan, another one like Louisiana, and then Minnesota, and some states were unenlightened, like California. California said, you're not going to put any money into this. You're going to have to pay for this yourselves. Well, most children's hospitals are teetering on being broke, so they can't afford to absorb the costs. The benefits accrue to Medicaid, not to the hospital. So, sadly, in California, despite the fact that we proved it out and we have the policy, the ill-headed Medicaid practitioners came up with a policy that makes no sense. They'll change their mind, but in the meantime, it still means this is as rare as a zebra in California. Florida's just about to flip. It's very exciting. And they probably will do what Michigan and Louisiana did, which is to reimburse the hospitals for their out-of-pocket costs to actually decode the genome. Next slide. Next slide. We got to skip some of these. Okay, so that's 10 years in what, 15 minutes? More than 15 minutes. Sadly, we're not done yet. This is not a universal panacea. Here's a great case. So this is a little baby who comes in with a stroke. Strokes are something you think about in old folks, like Shelley. Has anybody got holy water or something? Better sprinkle some on them. Anyway, this baby comes in with a stroke, and we decode the baby's genome, and it turns out it's an incredibly rare form of hemophilia. And so we're able to give the treatment for that. The factor that the baby's missing is factor 13A. We can give that to the baby, and the baby won't have any more bleeding. However, this baby is still paralyzed, partially paralyzed. Probably the baby will recover some function because the brain is still developing, but nevertheless, this is not a great outcome. What if we could have found that baby's condition before they developed the stroke? Wouldn't that make sense? Would that be possible? Let's not wait until the baby's in an intensive care unit to get a genome. Why not do it at delivery? Next slide. It gets worse. We have been doing a study now for 3 years. It's an NIH-funded study where we look at dried blood spots. Every baby in the US has a heel prick test. We collect drops of blood on a filter paper, and it's tested for a certain number of conditions. They are archived, and you can request them under very special circumstances. We did that. We've decoded 100,000 babies tried blood spots. And we started to analyze them, and here the slide shows results with 45 of them. They had genetic diseases. They weren't on their death certificate. The doctors didn't know. Why? Because getting a genome is still rare in California. And what was even worse, what really drives me nuts, is the number of those disorders were like the one I just showed you. That baby didn't necessarily have to die. So this gave us great impetus to move in a new direction. Next slide. So in the 1960s, these guys called Wilson and Youngner with the World Health Organization came up with criteria for what sort of diseases should we screen for in healthy babies that would be safe and not raise a lot of ethical issues and hopefully reduce infant mortality. And as a result of that, if we fast forward to today, there is a recommended uniform screening panel of 35 conditions that all babies are supposed to get, albeit each state makes up their own mind how many conditions they're going to test for in their babies. But what if we could just go, that's great, why don't we just do it for every condition that meets the 1968 criteria? So we spent 2 years looking at 7,300 diseases to figure out how many of them might fit the criteria. So far, we've got 434. No, we got 442. So we added 8 this week. 442 conditions. Next slide. So here's where we're at today. How do you develop a screening test for 500 genetic diseases using the same technology, using a blood spot, using the same genome sequencing instruments? It's completely different. This is a screening test. The baby's healthy. There's nothing to look for. There's no hoofbeats yet. The horse is still in the stable, so to speak. So we can't chase a phenotype. It needs to cost something very, very little, more than your weekly alcohol spend, but within reason. And we can't have a lot of false positives because overwhelmingly these babies don't have a genetic disease. And so we can't be chasing a lot of false positives. Whereas in a diagnostic test, as you can see, we can have it be a high price test because we have a very high diagnostic rate and we don't worry too much about false positives. So we are building this as we speak. First of all, we need a genome factory that can bash out genomes. We need to bash out 4 million, not 1,000 a year, as we do diagnostic genomes. That's tough. Main problem is to pay for it. Second of all, we got to use AI. Now, here's the thing. Just imagine for a minute. Let me see if I can think of a good example. Yes. Let's imagine if there were only 400 judges in the US, all right? And you've got 1 million folk who need to be prosecuted. How would you solve the problem? Well, let's say you had a robot that wasn't really good, right? So let's say it's right 95% of the time, wrong 5% of the time, but it can solve all the rest of those cases. Mightn't you do that to solve the problem? Or would you just go, no, these need to be perfectly tried. Let's only try the number that 400 judges can solve. That's the conundrum we're in right now. So AI is a solution that's infinitely scalable, but it's not perfect. It's not as good as a human being. Nevertheless, that's what we're looking for, is to tie AI, artificial intelligence, to the genome sequence so that we can identify as many babies as possible. And then the way to perfect it is really nice. AI is eminently trainable. You just need to churn through a few babies, and then it will be really good. So we need to get there. Next slide. So this year, unfortunately, I wasn't on PBS NewsHour, and I wasn't in the New York Times, and I didn't get a Guinness World Record. In fact, I'm not sure anybody even noticed it at all. But we published a paper 10 years later. And this one probably will have bigger impact because it proved out that you can actually do this and that the AI actually works well enough to move forward into clinical trials. So that's where we're at today. Next slide. And I put in 2032 there because that's probably where we'll be at in 10 years' time. It took 10 years for us to go from concept paper to Medicaid policies in half a dozen states. It'll probably take a similar period of time to go from concept paper to this being available for the population in half a dozen states. I think this is my last slide, my last data slide anyway. So I had a bit of fun. Shelley was getting worried though, because I didn't have my slides ready. And so he said, "Are you done yet?" And I said, "I'm just tinkering." He said, "Well, quit tinkering. Get over there and load it up." So this was my best thinking about tinkering. Where will we be in a decade? Well, I bet you we'll know 20,000 genetic diseases, not 7,300. I bet you we'll have 500 new gene therapies, not 5 or 10 or 20, whatever the number is today. It's not very many. I bet you that we will do genomes of birth and we'll reanalyze throughout the genome. And I'll show you what that looks like in a second. And then for those of you who are technology nerds, we'll be into long-read genomes and native methylation sequencing, other omics like metabolomics and transcriptomics, and lots of AI. Next slide. And this is probably what it's going to look like. It's going to be on an iPhone. Every mom, every dad has an iPhone these days, or some kind of smartphone device. I was in Africa this summer. I climbed Kilimanjaro. Everybody in Africa has some kind of smartphone as well. This is a ubiquitous healthcare delivery device. What we are trying to build out now is not just newborn screening, but healthcare delivery for rare and ultra-rare diseases via the smartphone. But some of the features are shown on the right. And let's change the mantra from what Professor Woodward said in the 1940s to what Professor Kingsmore says today. If you hear hoofbeats, don't bother thinking. Just order a genome. Next slide. That's it. So thank you to about 100 of our employees, both in the hospital and at the Institute. Thanks to our sponsors, and I noted some of them there, the Rady family, the Marriott family, the Preface family, and our other philanthropic donors. Thanks, KGI, for having me. Happy birthday. And Adeo Lumen Amicis Auxilium, to God for creativity, to friends for help. This is that multidisciplinary science that you saw talked about in the video. Thank you.
Thank you, Steve. That was wonderful. And I just want to go back and say that I still think Gator Gene was a good idea, but we'll get back to that. Dr. Kingsmore is willing to answer some questions if we have questions from the audience before we begin. She's in charge. I'm just going to shut up. My stroke.
Thank you. Is it on? Thank you very much for the illuminating talk. And in these outputs, you had referenced that there are roughly 500 or say 600, 700 genes that you can actually do something about. But there are probably 7,000 or even maybe 25,000 that we have characterized as variants of unknown significance, right? Unknown clinical significance. And when you sequence this, you're going to note where those variants occur and whether it matches up with the disease phenotype, such that you could alter a pathway of expression, or you could, in many ways, intervene with drugs independent of vitamin. Look at what was in there. So, how do you move the ball forward with American Society of Genetics or any of the groups, so that all this backlog of massive amounts of information is implemented in precision medicine at large?
Small question, huh? Easy one to start with. So there's a whole bunch of facets to that. So let's see if I can pull on you've got to match the great potential of genomic information with privacy and confidentiality, and the fact that these are babies, highly protected, and they have a life ahead of them. So you have to balance those two things. But as you can see in my slide, we are envisaging figuring out how to have a feedback loop. It does seem to make sense that each baby's data, if we can aggregate it and de-identify, could enrich every future baby's test. And this is true not just in terms of getting an answer, getting ultimately a diagnosis. This is also true in terms of drug development, as you alluded to, that for many of these diseases, we don't know enough about the disease to be able to design a drug today. With gene therapy, we have platforms that are amenable for many diseases, and the barriers are now what's the incidence, what's the indication, what's the progression rate. It's practical things that we can answer in that way. So that will be part and parcel of this, is thinking that through with like-minded folk, and that is actually happening. It's exciting. We're now about 10 groups worldwide, all trying to solve the same problem, and actively talking about how do we aggregate data that's de-identified and anonymized in a way that can benefit everybody without harming individuals. How did I do?
Hello. So I wanted to preface my question with 2 points. First, me and my fellow genetics classmates were very excited about the paper this year. So even if PBS wasn't watching, we were. And the other thing is that everyone in this room has some understanding of genetics, but that is different for everyone in this room, and even more different when you think about the general population. And so I think when you're consenting to have a whole genome sequence at birth, that is a lot of understanding that goes into that. And I wondered if you could speak on how we're going to increase the knowledge about genetics for everyone to consenting.
Another softball question. Thank you. So first of all, I think it would be very important to give your entire class an A. In perpetuity for all classes. Second of all, probably your class are part of the answer. One of the nice things about KGI, part of our partnership with KGI at the Institute, is you're training genetic counselors, and they are the glue, they are the folk who inform parents when they don't understand. And tragically, we have very few genetic counselors. I know Shelley wants to grow that program as fast as possible, but the practical constraints are they need places to be trained in to get their practical experience. But hats off to KGI for doing its bit. So that's part and parcel of the answer. But we need to educate a broad array of healthcare providers during their training, during their residencies, during their fellowships, to bring them up to speed. And we also need to educate the public. That's a lot of work. It's part of the reason I give talks, honestly, is to try to publicize this. Just simple ideas like genomes are good, not all variants are bad. You know, if you think about the last 2 or 3 years, everybody now knows what a genome is and DNA is, a variant is, a scariant, as Eric Topol calls them. So we just need to keep chipping away at this. That was definitely not a very good answer. It's right in line with what I'm getting paid for today.
I'm a medical device engineering secondary student, and of course, I'm always looking for that plug to devices. But for one of the first times, I don't have a device-related question. I'm wondering, could you speak to how the newborn screening can track prenatal, and how you could get the diagnostics with increased sensitivity and specificity with while decreasing the harm to the mother?
Oh, that's 3 in a row. Okay. All right. So the first bit's not that tough. The second bit, I have no idea what I'm going to do that at all, honestly. The first bit, yes, non-invasive prenatal testing. Well, you can get a blood sample from mom, and you can actually pick up the baby's DNA in mom's blood, floating around, cell-free DNA. And there are some really interesting proof of concept papers looking at, can we pick up genetic diseases? We've been able to pick up things like Down syndromes, what we call aneuploidies, chromosomal anomalies, for a while now, probably about the same period of time, about a decade. And that's become standard of care now to routinely test pregnant mums for those aneuploidies. But it's still elusive to be able to do it for these types of what we call single gene diseases or Mendelian diseases. I have just reviewed a paper that showed that it's possible. So that will be being published at some point here soon, and that horse will be off to the races. Now, this is not going to be easy at all, because you need to decode the genome very deep, because only a small percentage of the free DNA is from the fetus. And you need also mom and dad's genome. So it's not going to be a easy solution for most babies, unlike the newborn screen. But where you have a baby who's being seen in a high-risk obstetrics clinic, this makes a ton of sense. If you see something abnormal on ultrasound, if there's a strong family history, either of genetic disease or a fetal loss, it will make a ton of sense. I've forgotten what the second question is, very conveniently. It's about doing harm to mums. I don't even want to go there.
Steve, thank you. It was a wonderful talk. So
Thank you.
I'm trying to do you work? Do you have a big team? Do you have 1 million computers? I mean, you're getting tons and tons of data. How do you know that those are rare diseases? How do you know what to do? Do you get floored by the amount of to you?
I get pissed off all the time. I got so pissed off this morning that I was about ready to kick the dog. So it's very frustrating being a pioneer. I don't recommend it at all. There's no money in it. It's very frustrating, and you probably will get a stroke. So yes. No, I don't have an awful lot of money, and that's a big problem, because we need a lot of money to do this. It requires a team, right? So that's the trick. That's what's changed about science. Is it used to be about a professor who was this little god and had a team of slaves, and now we've realized that model doesn't work so well. A better model is multidisciplinary teams, and then the newer model on top of that is to embrace the commercial sector. So not all good ideas come out of academia. Furthermore, folks who are in the commercial sector tend to be more practical, more engineering, process driven, and think a lot about scalability and repeatability. And so that's the other piece. So what we've set up is a consortium of 25 entities, and most of them are commercial entities. And we have probably 100 people in 2 or 3 countries working on this. That's how you can do this large scale science. There are also many big efforts going on, like All of Us, or the UK Biobank. So we have genome information on at least 700,000 people right now, that as an investigator you can go and look at. That's a great proving ground for picking up what's a rare disease, what's a likely benign variant versus a pathogenic variant. We can do so much like that. It was completely unthinkable 5 years ago. Everybody's thinking about the drinks that are just about to happen.
They don't spend their money.
I'll ask you the last question.
Oh, you're going to ask me a really tough question. I know, Kiana.
So you talked about the potential of editing for and my concern, my question for you is that when do you think that will be happening? Because right now, even if we have a treatment for editing those genes, it'll cost so much to personalize editing for that specific disease. So where do you see that, and how do you think the price? We could decrease the price for those gene therapies.
Well, let's talk about the good news. The good news is it's now feasible to think about a gene therapy drug. This is feasible. There are lots of examples of it that work. They work economically, they work in terms of improved outcomes. Maybe not lots, but enough to know we are now in that era. We weren't in that era for the longest time. It took 20 to 30 years longer than most of us thought to get to that era. Now in that era, it has just started. It's extremely exciting. Many pharmaceutical companies are reinventing themselves around orphan drug indications. The FDA has revised its playbook to make it easier to get approvals for those drugs. We have an Orphan Drug Act, which gives economic incentives for drug companies to develop truly innovative medicines for rare diseases. So that's all good. You're right. The issue then is, how does a healthcare system afford these medicines, some of which cost more than $1 million? Yes, we can be saved Medicaid millions of dollars by diagnosing babies immediately, but maybe that will be offset by these therapies. I think there's always just a tension in medicine between the commercial sector and between doing good. And I think in the past we got there, and I think we'll get there again. So fundamentally, capitalism generally works, and I think it will generally work here. But I don't have a magic crystal ball to know exactly what the mechanics of that will look like. But I think we will start to see some kind of regulation related to drug pricing at some point soon in this country. We're kind of unique as a country that we don't. It's truly a free market. That's not the way it is, say, in the United Kingdom, where I grew up. Please rescue me.
Any other questions? I want to, on behalf of all of us, thank you, Steve. It was fabulous, and thank you for doing this, everybody. And I want to encourage everyone to come to the Chan Family Cafe, which is right down the hall here, and enjoy ourselves and talk with Steve informally, and have him get to know all of you, especially in the genetic counseling and genome data analytics folks. Make sure you meet Dr. Kingsmore and tell him who you are, because we do have alumni, I believe, working at Rady as well. So it's been a wonderful relationship, and we're thrilled to have Steve here. And I want to welcome all of you again. And thanks, Steve.